Great. So we're doing good, actually. We explained what a regression is and how it helps us predict the development of certain variables. In this lesson, we'll dig deeper and learn how to distinguish between regressions that are reliable and regressions that do not explain a large enough portion of the variability of the dependent variable. Are you ready? Good. Let's start then. We know for a fact that more than one variable determines the development of house prices. Yes, size is important. However, there are other important factors, such as location, neighborhood, year of construction. All these characteristics influence the price of a house. So, a simple regression containing only one variable will omit some important factors and will likely provide an estimate deviating from the actual price. This doesn't mean a simple regression isn't useful, because it can still have a high predictive power. However, we need to know it won't provide us an equation capable of estimating house prices with absolute precision. We can expect an error, and the regression model can be written as y equals alpha plus beta times x plus error. When we talk about sample observations, the errors are called residuals. In the XY plot from earlier, we can draw straight lines connecting the best-fitting regression line and the actual data points. And the distance of these lines will give us the residuals. The best-fitting line is a best-fitting line because it minimizes the squared sum of the distances of these residuals. If you draw a different line in this plot, its squared residuals will be higher than the sum of the squared residuals of the best-fitting line. This is the reason coefficients found with this technique are called OLS estimates. OLS stands for ordinary least squares. We need to find a line that minimizes the distance between itself and the actual data observations we are using to calculate a regression. Right. So, that's how we calculate regression coefficients and an equation that allows us to predict the independent variable. Before creating a regression, use your intuition. We need to think of the following question. Are all regressions equally good? Are there explanatory variables that do a better job in describing certain independent variables? There are. House size is one of the best indicators of house prices. Therefore, it makes sense to explore the relationship between the two variables through a regression. Does it make sense to use a regression between owner's age and house prices? Probably not, right? We don't expect buyers will be influenced by the age of the people who sell a house. Therefore, by definition, we can say all regression equations are not made equal. Some have an explanatory power higher than others. We need a tool that would allow us to measure such property and enable us to distinguish regressions with good, reasonable, and poor explanatory power. Fortunately, statisticians have come up with a tool that's easy to understand. It is called R-square. To understand R-square, we need to think of the total variability of the data, which is the measure for data dispersion and variability. Variance, right? Okay, so we'll use a concept very close to the one of variance, total sum of squares. TSS provides a sense of the variability of the data. The formula for the variance is the same, but n-1 is omitted. We've already calculated the sum of the squared residuals to obtain the regression coefficients. Therefore, we can obtain R-square with the following formula. 1 minus SSR divided by TSS. Typically, R-square is looked at as a percentage value, and it can range from 0 to 100%. The higher it is, the greater the explanatory power of the regression model. Typically, a simple regression with an R-squared of less than 10% has little predictive value. One-variable regressions with an R-squared of 30% or more are solid indicators of future performance.